Continuing the problems from yesterday, we're looking for possible inflection values, uh, actual inflection points, and intervals of concavity. So I don't feel like doing the derivatives for these because I think a graph would be a lot better if you know what the cube root of x looks like. All right, so hopefully you know it looks something like this. So it looks like possible inflection values would occur at x equals 0, maybe. And let's look at the actual value. Here we have concave up, here we have concave down. So there is an inflection point at 0, 0. And f is concave up like a cup from negative infinity to 0. And f is concave down like a frown from 0 to infinity. So that wasn't so bad since we had the graph. This one looks like it could be just as easy. When x is less than or equal to 0, we have negative square root of x, or the square root of negative x. So that would be this way. And then over here, x squared. Well, looks pretty easy. Possible inflection value at x equals 0. Looks like it might change there. We actually do have an inflection point at x equals 0. And if we had to plug that in, that would be at 0, 0. So I'll write that. Inflection point at 0, 0. And in this case, y is concave down like a frown from negative infinity to 0. And y is concave up like a cup from 0 to infinity. All right, so now we're going to connect this idea with an idea of relative extrema. We can use the first derivative test, and remember that said if the first derivative changes from positive to negative, then there would be a relative maximum there. If f prime changes from negative to positive, there'd be a relative minimum there. Sometimes we don't have that information. We only have information about the second derivative. So in that case, we're going to use the second derivative test. So if f double prime is positive, if f is concave up like a cup, then there's going to be a local minimum at this critical value. If f is concave down like a frown, there's going to be a relative maximum at that value. And if the concavity is 0, we can't tell anything, so we have to use the first derivative test. Okay, so let's just jump in with that. We're going to use the first derivative test to find the relative extrema, and then we'll use the second derivative test. So in order to use the first derivative test, we need the first derivative. So f prime of x equals negative 15x to the fourth plus 15x squared. If we set that equal to 0, and let's factor out 15x squared. So we'd get negative x squared plus 1. All right, so our numbers that we're going to check, we have 0. Well, I guess I should have done it this way. All right, I don't like the way it looks. Let's try that again. We have negative 1, 0, and 1. These are x values, and we're checking the sign of f prime. If we plug in different numbers, it looks like we would get negative, positive, positive, negative. Okay, so then what does that tell us about f? F has a relative min of, and now we have to plug in the values, so we have a relative minimum there at x equals negative 1. If you plug that in, f of negative 1, so what would we get? Looks like that would be negative 2. So f has a relative min of negative 2, and we'll say at x equals negative 1, since f prime changes from negative to positive there. All right, and f has a relative max at x equals 1. I guess we have to tell what that is. f has a relative max of, if we plug in 1, we get 2 at x equals 1. And that's because f prime changes from positive to negative at those values. Now, we should get the same answers with doing the second derivative test. All right, so let's change this. So we have second derivative, f double prime of x. That would be what? Negative 60x cubed plus 30x. Factor that. Let's see where it equals 0. Take out a 30x. Actually, I'm not going to waste my time factoring. Here's what we need. We need the critical values, which we already know what they are. From the last problem, we know that the critical values are at x equals negative 1, 0, and 1. So let's just check the sign of these. If we plug in negative 1 for the first part, this would be, sorry. All right, I don't even care what the number is, but if we plug in a negative 1, we're going to have a positive value. If we plug in 0, we're going to get 0, so that doesn't tell us anything. And if we plug in 1, we would get a negative value. So now we're going to have the same answers, but we're going to justify them differently. So if we're using the second derivative test, we would say f has a relative min of, and we'll say the same thing, negative 2 at x equals negative 1, since f double prime of negative 1 is positive. Okay, and it was a critical value, f prime of negative 1 equals 0. Okay, similarly, f has a relative minimum value, a relative maximum value of 2 at x equals 1, since f double prime of 1 was less than 0. All right, so let's look at this. This time we don't have a function, but we do have a table. And remember, we like to mix these up. Sometimes we get graphs, sometimes we get tables, sometimes we get functions. And so this time we're just looking at a table. So take a look at it, and f is a twice differentiable function. I'm sure that's important. And it's continuous on the interval. Is it safe to say that f of x is concave up on the interval from negative 3 to 5? Well, at the two values we notice, or these are positive, this is 0, but the endpoints don't really tell us much. So we know that at x equals 2, f double prime is positive, but does that tell us anything about any of the other ones? No, not really. So no. We don't know the signs of f double prime on the interval except at x equals 2. All right. Review. These are always good, right? Explain why there must be a z on the interval from negative 3 to 5 such that f of z equals 6. Well, we know that f is continuous because it told us that. Okay, and let's see. This could maybe be the IVT, the MVT. Let's try to find some values out. F of negative 3 is 0, and f of 5 is 7. So there has to be, I'm not going to write all this out just because it takes me longer to write it. There must be, or there exists some z on that interval such that f of z equals 6, since 6 lies in between 0 and 7. Okay, so since we go from a y value of 0 to a y value of 7, and it's continuous, it has to hit 6 somewhere. Okay, that's what we're saying. I'm going to clear some of that out so I can talk about this part. All right, so, and we know that by the IVT. It's the intermediate value theorem. Since this one's review, I bet we're going to use the MVT, but that's just my guess. We're talking F prime, so we're talking slope here. We know that F is continuous on the interval. We also know that F is differentiable because of up here it said it was twice differentiable. So now, do you remember the MVT? It had something to do with slope. It was saying that algebra slope has to be equal to calculus slope somewhere. Now, if we plug in those values, f of 5 is 7 minus 0 over 8. Hey, look, that's 7/8. So then, yes, there must be some w on the interval between -3 and 5 such that f prime of w equals 7/8 by the MVT. Mean value theorem, talking about slopes. All right, and the last thing that I think we'll look at today, does f have a local max, a local min, or neither at x equals 2? All right, well, we do know that, oh, I better change colors. Yeah, this is an awful color. We'll go with it. Now, we do know that f prime of 2 equals 0, so that makes it a critical value. And we know that f double prime of 2 is positive. So using the second derivative test, we know if it's concave up like a cup, remember, we have a relative minimum. And that's because of these reasons. All right, so that concludes this video. I think we'll have one, maybe two more for this section. Guess we'll find out.